Okay. Good evening to all. Good evening, dear students. Are you ready? So, welcome to the session. Oh. Yeah. Yes. Okay. Yeah. So let us start this today's session. In the last class, we have discussed about the conditions for parallel operation of alternates. No? Condition for parallel operation. The voltage must be same, frequency must be same, and phase sequence also must be same. Phase sequence and phase rotations must be same. If not, what happened? In all the conditions, there exist circulating currents. Circulating currents takes place between the two systems. So alternators are nothing but they are the voltage sources. No? These alternators are nothing but voltage sources. Just like two batteries are connected in parallel. If they are unequal voltages, what will happen? Circulating currents. Therefore, if a terminal voltage is not same, then also, but frequency is not same, then also vector potential difference will come into picture. Vector difference. No? Though magnitude is same, AC components, no? When phase are different, that will causes the circulating currents. And also phase sequence must be same. If phase sequence is not same, then also circulating currents will come into picture due to vector potential difference. Right? Yeah. So yesterday we have seen all the conditions and how to verify all the conditions also we have discussed. So there are lamp method, right? So one lamp and two lamps are bright, one lamp dark, or three lamps are simultaneously dark and simultaneously bright, that we have seen. Okay, yeah. But in difference between the first one, three lamps simultaneously dark means there we are connected the lamps across the same phases, between the same phases. If phase sequence is same, then what will happen? All the three lamps will be simultaneously dark, simultaneously bright. If lamps are connected between the same phases, if all three lamps are dark and bright simultaneously, phase sequence is correct. Okay. If phase sequence is wrong, say they are not, never be simultaneously dark, never be simultaneously bright. And coming to the next method, lamps are connected between the two different phases, cross connected, and further we have observed that if one lamp is dark, other two lamps are equally bright, then the phase sequence will be, then the phase sequence will be same. Okay. So these things we have discussed. The synchroscope is a meter. Synchroscope is a meter that will measure the phase sequence as well as frequency. So I am not going to discuss the phase sequence. It is a simple device and there is no scope to ask any question on synchroscope. Right? And if you want, you can find any measurement textbooks, the synchroscope. And even I have given the material, you just to go through those who are interested. Right? Yeah. Now, in this class, let us start the next parallel operation of alternator, continuation of parallel operation of alternator. Yeah. The very beginning of the parallel operation of alternator, I have told that minimum number of alternates in parallel and maximum number of alternates in parallel. Minimum and maximum. So what are the minimum number of alternates in parallel? 2. Minimum number of alternates is, that is 2 alternates in parallel. And maximum, infinite number of alternates in parallel. Okay, infinite number of alternates means the alternator is said to be connected to the infinite bus bar. So in parallel operation, we are going to see under two headings. One is 2 alternators. Minimum number of alternates are connected in parallel. That is 2 alternates in parallel. And maximum number of alternates in parallel. That is said to be infinite bus bar. Okay, yes, 2 alternators, minimum number, maximum number. But during these two cases, the conclusions are different. Conclusions are not same. Behavior of the machine is also not same. So we have to observe what exact difference is between two alternators. A finite number of alternators are connected, and alternator connected to an infinite number of alternators. Okay, so we are going to see very clearly, and we will observe. We are going to finalize the conclusions. With the general conclusions, you can able to answer for any questions is given. Okay. So first, let me start with the two alternators in parallel. Two alternates in parallel. Two alternators two alternates in parallel. Minimum number of alternators, two alternates in parallel. And for this, and again, when two alternates are connected in parallel, we are going to see under the two headings. So for example, first we are going to see under no load condition, two alternates in parallel. First under no load condition. See, two alternates in parallel. Two alternates in parallel. First, I will take under no load condition. Let us discuss first under no load condition. After that, we will come to the load condition. No load condition. See, these are the two alternators that are connected in parallel. So this is alternator 1. This is another alternator connected in parallel. But no load. Load is not there. Simply it is open circuited. Open circuited. Yeah. So these are the two alternators connected in parallel. Right? This is ZS1, and this is ZS2. Impedance of the machines. And these are the E1. Generated EMF is E1. This is generated EMF E2. Generated EMF is E2. This is the terminal voltage V. Terminal voltage V. Okay. Terminal voltage V. And its frequency EF. Okay. Yeah. Right. Listen. These are the two prime movers. Just a minute. Yeah. So these are the two prime movers of its individual prime movers, alternators. Load is not connected. Say the E1 induced EMF of E1, first generated EMF is E1. Say if this E1 is equal to some 400 volts, E2 also equal to 400 volts. Say then there is no current here, no? There is no current. There is no current to the load, and there is no current to the load from the alternator 2. And also there is no circulating currents between these two. There is no circulating currents between these two. So no load condition means what is the V? V also equal to same. V also equal to 400 volts. 400 volts. And see, frequency is 50 hertz. For example, frequency is 50 hertz. Fine. This is no load. Now, under these conditions, what we are going to see is alternates connected in parallel. Again, we are going to see under two cases. Case 1, effect of change in excitation and effect of change in mechanical power input. So, in our alternator, how many inputs are there? Alternator is said to be doubly faded machine. Doubly faded. Doubly faded means one is excitation, another one is the prime mover input. So for these two cases, if excitation of alternator changes, what happened? If prime mover input changes, what will happen? That we are going to see. Load is kept the same. Load is kept constant, right? Load condition that we are going to see, of course. But no load condition, what are the disturbances are possible? Or what are the controlling is possible on the machine? The controlling on the alternator input side. That is excitation and prime mover. Two inputs are there now? Yes. So if excitation changes, what happened? Prime mover changes, what happened? So first let us see effect of change in excitation. So we are going to see under two headings. Number one is effect of change in excitation. When excitation changes, what are going to be happen? Second case is when prime mover input changes, what is going to happen? So first let us see effect of change in excitation. Case 1. I am taking case 1. The effect of change in excitation. Effect of change in excitation. If excitation changes, what is going to be happen? Case 1. See, two machines are operating at 400 volts, say 400 volts. If terminal voltage of incoming alternator increases, terminal voltage increases, E1 increases to E1 dash. E1 increases to E1 dash. And first of all, these terminal voltages, see the generated EMF of first machine, I can draw like this. The phases, phasor of E1, this is phasor of E1, and this is phasor of E2. E2, both will be taken in phase opposition with respect to local circuit. Local circuit in the sense, if you take in between this, the two voltages, the potential difference is said to be 0. If this is circulate giving the current here and this is giving the current here, okay, and both currents are in phase, but any currents inside of the circulating currents, dear students, let me make this point is very clear and concentrate. When currents are going to the load, say if it is corrected, both currents are additive, fine. But when current is circulating inside of the machine, for example, when excitation increases, say it is at a higher potential, when currents are circulating, this current is upwards direction, but for this the current is downwards direction. Any currents are circulating, one act as a generator, other one act like a motor. It is giving the current, it is taking the current. So with respect to local circuit, I can take E1 and E2, both will be taken in phase opposition. Right? Yeah. And even you can also take in phase also, does not matter. Later I am also going to show E1, E2 can be taken, both will be in phase also. So you will get both conclusions are same. But with this phasor, we will get the conclusions easily. So this is, understanding is easy. And those who are expressing a doubt say, sir, why not E1 and E2 will be taken same? Yes, you can also take E1 and E2. There also you will get the same conclusions. With respect to load circuit, if you take with respect to load, both currents are aiding. This is also giving the current, this is also giving the current. Both are aiding. I can take E1, E2 in same phase. But with respect to local circuit, say E1 and E2, I can take in phase opposition. But in both way, you will get the same conclusions. First, let me explain this. This is E1 and E2. Both are said to be in phase opposition with respect to local circuit because one is giving, other one is taking. Now, if excitation of machine 1 increases, if excitation of the conclusion is, if excitation of machine 1 increases, what will happen? If excitation of machine 1 increases, E1 increases. Excitation of machine 1 increases, E1 increases to E1 dash. E1 increases to E1 dash, say. That is some more than 400. More than 400. See here, if it is E1 dash is equal to some 450 volts, generated EMF has increased. We are increasing excitation of first machine. When excitation or field current of first machine is increased, its generated EMF increase to 450 volts. And this is, I am not changing. Second machine, we are keeping same. Only excitation of first machine is increased. And when excitation of first machine is increased, what is going to happen? There will be circulating current between these two. Because even at higher potential, there is a circulating current. There is a circulating current. That circulating current is ISY. Correct? The circulating current is ISY. Synchronizing current. But when excitation of any one machine increases, the disturbance we are giving. Excitation increases means, first of all, I will ask a doubt for you. See, initially before disturbance, this terminal voltage is 400. No? This terminal voltage is 400 means, what is this voltage? This voltage also 400. Initially, this also 400 volts. This is 400 volts and this is also 400 volts. Right? Terminal voltage is 400. Then only stable parallel operation. Terminal voltage of two machines must be same for stable parallel operation. Now what we are doing, if excitation of machine 1 is increased, E1 increases. And when E1 increases, this terminal voltage also will increase. No? First machine excitation is increased, then terminal voltage of first machine also will increase. But when terminal voltage of first machine is increases, how second machine terminal voltage will increase? How second machine terminal voltage will increase? How stable parallel operation is achieved? How voltage stability takes place? Then synchronizing power will comes into picture. I told in the last before class. Synchronizing power, when disturbance condition, synchronizing power will comes into picture. And the synchronizing power is reactive power for change in excitation. We are going to see that this is synchronizing current and synchronizing power will comes into picture. It will maintain the synchronism. It will equalize the set terminal voltages. How it is doing that we are going to see. Now, what is the role of the synchronizing power? How it is maintaining the terminal voltages are equal. That we are going to see. Right? Yeah. So, this currents, ISY is coming, but ISY is delivered by the first machine. Huh? Yes, ISY is delivered by the first machine, whereas ISY is absorbed by the second machine. ISY is absorbed by the second machine. Now, this ISY is equal to how much? ISY is equal to, can I say, E1 dash minus E2 divided by ZS1 plus ZS2 in the circuit. Apply KVL. Potential difference is E1 dash minus E2. Okay, yes. Now ZS1 divided by ZS1 plus ZS2. Or, see, for this equation, listen, equation, in this loop equation, how I can write? V same, terminal voltage is same. V is equal to E1 minus ISY into ZS1. E1 minus ISY into ZS1. But this is E2 lower potential compared with V. So, the equation is V terminal voltage. Terminal voltage is equal to first machine E1 minus ISY into ZS1. That is equal to E2 plus ISY into ZS2. Correct. First machine higher potential. So E1 minus drop is equal to V you are getting. But second machine, it is lower potential compared with V. So that will be E2 plus ISY into ZS. From this, yeah, E1 E1 minus E2 is equal to what? Or else for same equivalent ZS is same say. Let ZS1 is equal to ZS2. ZS1 is equal to ZS2. So this is ZS, that is equal to E2 plus ISY into ZS. ZS. Then E1 minus E2 is equal to what? E1 minus E2 is equal to 2 into ISY into ZS. Therefore, what is ISY? ISY is equal to E1 minus E2 divided by 2 ZS. 2 ZS. That is nothing but E1 minus E2 divided by ZS1 plus ZS2. Of course, this much discussion also not required. So what is potential difference? E1 minus E2 divided by ZS1 plus ZS2. That is the synchronizing current. This is the synchronizing current. Synchronizing current. Now you find out V value. Now V is equal to what? V is equal to E1 minus ISY into ZS1, or that is equal to E1. E1 is equal to minus ISY is equal to how much? E1 minus E2 divided by ZS1 plus ZS2. Or simply let me take it is 2 ZS. 2 ZS into this is also equal to ZS. ZS. I am taking impedances are equal. ZS. From which equation? From this equation I am taking. So E1 minus the ZS will get cancel na? E1 minus E2 by 2 plus E2 by 2. That is equal to what? E1 plus that is E1. E1, yeah, E1 by 2 plus E2 by 2 na? Yes, E2 by 2. Therefore, from this relation, V is equal to what? V is equal to, we have got V is equal to E1 plus E2 by 2. E1 plus E2 by 2. V is equal to E1 plus E2 by 2. But we have increased E1, na? E1 increased to E1 dash. When E1 increases, what will happen? V also will increase, na? Yes. When V increases, E1 increases. Or else, initially if you take E1 same, now I can take this is E1 dash. For example, when we are increasing excitation, E1 dash. And this is E2 same. E2 I am not increasing. E1 dash. Okay. This is E1 dash. E1 dash. Wherever E1 is there, after increasing, it becomes E1 dash. Okay, E1 dash, E1 dash. Fine? Yeah. This is E1 dash, E1 dash, E1 dash. E1 dash plus E2 by 2. E2 by 2. So, the conclusion is, listen. This equation is clear, na? Yes. The conclusion is, when excitation of any one machine increases, if I am increasing excitation of first machine, say, terminal voltage will increase. Terminal voltage is not 400. This is also going to be increased. Terminal voltage also will increase. This also will increase. This also will increase. How much that is equal to? V is equal to, as I have given, E1 dash plus E2 divided by E1 dash plus E2 divided by 2. The voltage will increase. When excitation of machine 1 increases, terminal voltage increases. And this V will increase. V will increase. And two terminal voltage will be equalized. Let me explain and what is the mechanism is going on inside of it. Yeah. When excitation of first machine is increases E1. Initially both are same, na? Initially E1, E2 both are in phase opposition with respect to local circuit. But when excitation of machine 1 increases, E1 increases to E1 dash. E1 increases to E1 dash. Let me take in the next page. Yeah. When excitation increases, when excitation of machine 1 increases, when excitation of machine 1 increases, then E1 increases to E1 dash. E1 increases to E1 dash. Right? Yeah. This is E. E1, E1 dash. But now E1 dash is increased. This is E1 dash. E1 has increased to E1 dash. E1 dash. Then potential difference. Potential difference. That potential difference is ESY. I can say this is E1 dash minus E2. That is equal to ESY. Synchronizing voltage. Synchronizing voltage, ESY. ESY is equal to difference of this. That is ESY. And when this is ESY will be along the bigger vector because E1 dash is more, no? E1 dash is greater. That's the reason ESY also along the bigger vector. When that is ESY, this will be the ISY. This is ISY. ISY lags the ESY by 90 degrees always. ISY always lags ESY by 90 degrees. ISY always lags ESY by 90 degrees. Why? Because ISY circulate in pure reactive circuit. Because it circulate in the armature windings. It circulate in the armature winding. So which is pure inductive circuit. The circulating the armature winding means reactance, na? So due to reactance, it is reactive circuit, pure inductive circuit. ISY lags the ESY by 90 degrees. This is fixed always. Are you getting? Why? Because this ISY is circulating inside of the machine. So resistance is negligible, say. When resistance is neglected, so it is pure inductive circuit. Armature winding is pure inductive circuit. Therefore, current lags this resultant voltage by 90 degrees. Okay? Yeah. And from this relation, you see, with respect to machine E1 and E1 dash, ISY lags the E1 or E1 dash by 90 degrees. ISY lags the E1 or E1 dash, say. The first machine voltage, E1 or E1 dash by 90 degrees. Therefore, machine 1 operated ZPF lagging. And armature reaction. Therefore, armature reaction in machine 1 is purely demagnetization. Armature reaction is purely demagnetization in machine 1. Purely demagnetization in machine 1. Similarly, ISY leads the E2 by 90 degrees. If you take here, ISY leads the E2 by 90 degrees. So therefore, second machine operated ZPF leading. ISY leads the E2 by 90 degrees. ISY leads the E2 by 90 degrees. Therefore, machine 2 operated ZPF leading. Armature reaction is purely magnetization. Armature reaction in machine is purely magnetization. Due to synchronizing current. Load current is not there. Only the current is circulating. That is synchronizing current. Synchronizing current is also armature current. Na? Armature current. It will magnetizes and demagnetizes. It is demagnetizing the first machine and magnetizing the second machine. Magnetizing the second machine. Now synchronizing voltage is there, synchronizing current is there. Is it active power or reactive power? Let us see. The synchronizing power is synchronizing power. Synchronizing power PS1 say. PS1 is equal to active power I am taking E1, that is nothing but E1 dash into ISY cos 90. Its power factor angle is cos 90, no? Yes. Cos 90. You're getting ISY is common for both machines, na? First machine is generating the current ISY. So angle between E1 and ISY 90 degrees, lagging. So that is nothing but it is 0. 0. Similarly, PS2 for second machine also it will be for PS2 is equal to E2 into ISY cos 90. That also equal to 0. That also equal to 0. I mean to say synchronizing power is not the active power. Synchronizing power is not active power. Synchronizing power is not the active power. Active power. But it will be reactive power. If you see synchronizing power QS1 is equal to E1 dash and ISY sin 90. Sin 90. That is equal to E1 dash and ISY. Similarly, QS2 is equal to E2 into ISY is also sin 90. Reactive power is nothing but voltage into current into sine of the angle. Sine, that is reactive power. Active power means cos of the angle, cos component. Sine component is reactive component. That is equal to E2 into ISY. Therefore, synchronizing power is the reactive power. Synchronizing power is reactive power. Synchronizing power is the reactive power. These are the very important conclusions. I am going to make very key point. With that key point, load condition is going to be very simple. Load condition is very simple. We are going to see the questions how it will be. If you catch the conclusions, you can think any question is being given based on the conclusions we can able to answer. That's the reason I am writing point by point. Okay. Yeah. So synchronizing power is reactive power. Right? Do you remember first of all what is the synchronizing power? We have discussed before class. Synchronizing power coefficient and synchronizing power. Synchronizing power yesterday itself we have discussed. Synchronizing power will comes into picture when the machine is subjected with some disturbance. It maintains the synchronism. How it is maintaining, we are seeing now. Okay. Yeah. Coming to the original diagram, let us see how synchronizing current is equalizing the potentials, voltages. See. Now coming to the circuit, initially 400, 5. No circulating current, nothing. What we have done, excitation of first machine is increased. So therefore its voltage is increasing. Now what it is doing, synchronizing current is coming into picture. It is higher potential. Na? Synchronizing current is coming into picture. Synchronizing current is delivered by the first machine, absorbed by the second machine. Delivered and absorbed by the second machine. But the synchronizing current is it I sin phi component or I cos phi component? I sin phi component. Because I cos 90 0. This is reactive component. Is this ISY is armature current or not? That is armature current only. In our machine only two currents. What is one current? One is the field current, another one is armature current. But that armature current only, namely we are calling it as the synchronizing current. So the synchronizing current circulate Synchronizing current is reactive current, reactive power. So therefore, first machine is delivering the reactive power, second machine is absorbing the reactive power. So that synchronizing power is the reactive power delivered by first machine, absorbed by second machine. And what reactive power will do? Reactive power will produce as the flux. Active power will produce as the torque. Well-known thing, no? Reactive power will produce as the flux. Active power will develop the torque. So as this is the reactive power, and this reactive power will produce as the flux, this current will produce as the flux in opposite direction to the first machine. It is demagnetizes the first machine. And for second machine, the flux is adding, magnetizing. Okay? The armature reaction in first machine, demagnetization, second machine, magnetization. Magnetization. Right? Yeah. So, by demagnetization and magnetization, what is going to be happen? This effect will reduce. This is not 450. It will reduce. It will reduce. And this will be increased. This is increased. But the difference is there, na? Magnetization. So first both are 400, 400. Now it has increased. But synchronizing power, it is demagnetizing and it is magnetizing such that again set terminal voltages are equalized. And what for it is doing? It is reducing the difference between these two such that set terminal voltage will be equalized. But no doubt, set terminal voltage is going to be increased. It is going to be increased. Set terminal voltage, what is this? E1 plus E2. It will be increased. Say for example, it may be some 420 volts. For example, it has increased. Set terminal voltage will increase. Here important conclusion is, if excitation of any one machine is increases, set terminal voltage will increase because E1 dash plus E2 divided by 2, na? Yes, set terminal voltage will increase. And vice versa also correct. If excitation of any one machine is decreased, set terminal voltage will also decrease. Increases, increases, decreases, decreases, vice versa. But I want to maintain again this voltage as 400 volts. What to do? Tell me. It is increased, na? This voltage is increased to 420 volts. 420 volts. Fine. But still I want the same voltage. Excitation of machine 1 is increased. Again to maintain the same terminal voltage, what you have to do? Decrease the excitation of second machine. Now you need to decrease. It is not 400. Still you have to decrease. Why? Because E1 is increased, then E2 has to be decreased to maintain the same terminal voltage. Okay? Yes. There is a question. What is the question? You know, previous examination, two alternators, G1 and G2. Two alternators, G1 and G2 are connected in parallel. If excitation of G1 is increased, to maintain the same rated terminal voltage, excitation of G2, the second machine, excitation of G2 has to be decrease, increase, no change, like that. What to do? Excitation of second machine has to be reduced. Opposite action. What we have to do is, we have to do it is a opposite action. When increases, it has to be decreased. From this equation, you just think about to maintain the same. And question also, if only excitation of one machine is increases, what will happen? Definitely set terminal voltage will increase. If to maintain the same thing, you need to decrease excitation. Okay, practical cases, we want rated voltage. Why we will do this? Increase in excitation means reactive power changes. But I want to, the question in previous examination, the reactive power, to shift the reactive power from second machine to first machine, what to do? To shift the reactive power from second machine to first machine, what to do? Increase the excitation of first machine. So it will take the more reactive power. Reactive power sharing is more proportional to excitation. Okay, yeah. So who is equalizing the set terminal voltages? Synchronizing power. Synchronizing power is coming. It is demagnetizing first machine, magnetizing the second machine, such that, so initially both are same, but when excitation is increased, voltage increases. To maintain the same thing, it is demagnetized and this is magnetized. Set terminal voltage will be equalized. So synchronizing power is doing equalizing the set terminal voltages. Okay, both the terminal voltages are going to be, this is also 420 volts, this is also 420 volts. Both are equalized, but both is increased. Terminal voltages are increased. See, one general statement. During parallel operation, okay, overexcited machine will be always demagnetized. Very important conclusion is not only here, everywhere you take. And during parallel operation, I'm going to write all the conclusions. First listen. During parallel operation, an overexcited machine will be always demagnetized. Underexcited machine must be magnetized. Then only is voltage stability. Overexcited machine has to be demagnetized. Underexcited machine has to be magnetized to reduce the differences of these two. Who is doing this? Synchronizing power is doing. Okay. And who is the responsible? Who is the responsible for the synchronizing power? Tell me. Synchronous reactance. Due to synchronous reactance only, ZS or resistance you neglect. Synchronous reactance only, current ISY lagging. So synchronous reactance is responsible for the production of the synchronizing power. Synchronizing current, synchronizing power. That's the reason it is lagging. Okay. So it is reactive power is coming. Synchronizing power. The synchronous reactance is responsible for the synchronizing current. That's the reason X by R ratio should be more. Synchronous machine generally they will also design with large X by R ratio. When X by R ratio is large, the machine is more stable. When X by R ratio is more, so stable parallel operation. For stable parallel operation, the machines will be designed with large X by R ratio. X by R ratio. The resistance will be less, reactance will be more. Fine? Yeah. Now listen. Before writing all the conclusions, let me brush up all these things, whatever we have discussed so far. Now you forget about these numericals. Some value I am increasing, decreasing, forget about. Final conclusions, what we are going to write, they are important. And let me brush up within a minute, whatever we have discussed so far. My dear students, see, initially two machines are operating. Both are same generated voltages. Terminal voltage is also some 400 volts. 400 volts. But when excitation of first machine is increases, this E1 increases. Now there will be synchronizing current. Due to potential difference, synchronizing current will comes into picture. And the synchronizing current is reactive power. I sin phi component. And the synchronizing current is delivered by the first machine, absorbed by the second machine. And the synchronizing current or synchronizing power demagnetize the first machine of whose excitation is increased. Demagnetize the first machine because excitation has increased, and magnetize the second machine such that set terminal voltages are equalized. Okay. When excitation increases, it is demagnetizing, it is magnetizing. Set terminal voltage will be equalized. And during parallel operation, an overexcited synchronous machine will be always demagnetized. Underexcited machine will be always magnetized. And if excitation of any one machine is increases, set terminal voltage will increase. And vice versa. Decreases also. But to maintain the same rated voltage, again I want it has 420 na? Again I want to maintain same 400. What to do? Decrease the excitation of other machine. Opposite action. Decrease the excitation of other machine. And synchronous reactance is responsible for the production of the synchronizing power. So that's the reason machines are designed with large X by R ratio. For stable parallel operation, X by R ratio should be more. Okay. So let me write all these conclusions. See, if the excitation of machine 1 increases, if the excitation of machine 1 is increased, then the synchronizing power will comes into picture. will comes into picture, which is reactive power. Or first let me talk about synchronizing current. Then, okay, if the excitation of machine 1 is increased, then the synchronizing current, then the synchronizing current or power, synchronizing current or power will demagnetize the first machine, machine 1, of whose excitation is increased, and magnetizes the other machine. Magnetizes other machine. That is machine 2. Magnetizes other machine 2. Such that set terminal voltages are equalized. For stable parallel operation. Next. If the excitation of machine 1 is increased, then the set terminal voltage will increase. And vice versa. Decreases means also decreases. Decreases. Okay. Yeah, and vice versa. See, once no load conditions are completed, full load conditions are set to be completed. There is no discussion. Here only we are discussing everything. Yeah. If the excitation of machine 1 is increased, then the set terminal voltage will increase and vice versa. But to maintain the same rated voltage, to maintain same rated terminal voltage, decrease the excitation of other machine. Decrease the excitation of other machine. Okay. Yeah. Decrease the excitation of other machine. Now, during parallel operation, an overexcited, general statement this is, an overexcited synchronous machine. An overexcited synchronous machine will always demagnetized, and an underexcited machine, will always magnetized. For stable parallel operation. Okay. This is general statement. Overexcited machine will be demagnetized, underexcited magnetized. Who is doing this? Synchronizing power. Of course, that synchronizing power is itself reactive power. Synchronizing power is a reactive power. Okay. Now, the synchronizing power is reactive power. When change in excitation causes, synchronizing power will be reactive power. When excitation changes, the synchronizing power will be reactive power. The synchronizing power is reactive power. Reactive power. Now, and synchronous reactance. Synchronous reactance is responsible. Synchronous reactance is responsible for the production of synchronizing power. Synchronizing reactance is responsible for the production of synchronizing power. Due to synchronous reactance only, ISY lags by 90 degrees. Synchronizing power. Therefore, the machines will design with a large X by R ratio. Large X by R ratio for stable parallel operation. For stable parallel operation. For stable parallel operation. Okay? Yes. Stable parallel operation. Fine. So all this discussion I have given when two phases are taken opposite direction, E1 and E2 taken opposite direction. Yes. With respect to local circuit. And if you take with respect to load circuit also, it will be same. Note. If E1 and E2 is taken in same phase with respect to local circuit, what will happen? See, let me draw. You will get the same conclusions. If this is E1, dear students, this is E1. This is E1 and this is E2. Both are in same phase. E1 and E2. Both are in same phase. Earlier I have taken in phase opposition. E1 and E2 same phase. Now, there is no circulating current, there is no synchronizing current. But when excitation of first machine is increased, E1 increased to E1 dash. This is E1 dash. E1 dash. When that is E1 dash means this is ISY. This is ESY. Correct? This is synchronizing voltage. That will be E1 dash minus E2. E1 dash minus E2 is equal to ESY. ESY is here. This much ESY. That will be ESY. When that is ESY, ISY will be compulsory. It lags always. This is ISY. This is ISY. But this is ISY with respect to machine 1. With respect to machine 1, ISY in this direction. But with respect to machine 2, we have to take ISY opposite direction. We have to take ISY with respect to machine 2 in opposite direction. Why? Why? Because first machine is delivering the current, second machine is absorbing the current. Correct or not? For generator, first machine ISY is giving, second machine ISY is taking. Taking in the sense, actually its current is reverse direction. Reverse direction. Reverse direction. So, if you take E1 and E2 in same direction, then IS1, IS2, you have to take in opposite direction. For ISY, for machine 1 and machine 2 to be taken opposite. But earlier I have not taken. Why? E1 and E2 already we have taken opposite direction because first machine acting as a generator and second machine acting as a motor opposite direction, then the current is no need to change. But if you take both in same direction, current has to change, because one is giving, one is taking. One is acting like a generator, other one is acting as a motor. Current to be taken opposite direction. Then also same conclusions you are getting now. Then also you can get the same thing. With respect to this, with respect to machine 2, it is 90 degrees leading. Then ISY. From this, what you understood? ISY leads. ISY lags E1. Lags E1 by 90 degrees. By 90 degrees. Therefore, machine 1 operated what power factor? ZPF lagging. ZPF lagging. Similarly, ISY leads. ISY leads E2 by 90 degrees. Therefore, machine 2 at ZPF leading. ZPF leading. Now all the conclusions will come to the same. Therefore, all the above conclusions, all the conclusions will be same with earlier case. Will be same. All conclusions will be same. Okay. You can take any way. You can take both in same direction, opposite direction. Does not a matter. Okay. Yeah. Fine. Yeah. Can you tell me any doubts are there on this? Just before going to, then no load condition is important. Load condition, no explanation. Directly I will say there, I can take it as synchronizing current is reactive power. With that I will proceed. Any doubts on this? Please tell me. Just for 5 minutes and then we will go. Any doubts? Hello? Any doubts? Hello? Hello?
Good evening.
Good evening, tell me.
Sir, I have that when E1 increases, when E1 means that 400 volt will be go to 420 volt.
When E1 increases, see.
Means that terminal voltage will also increase.
Increase, yes. Second machine terminal voltage also increase. Why? Why? Because this E2 also will increase. Fine. This equation, with this equation I am taking. This is 420. This is also will be 420. First of all, can you tell me both are same points or not? This is increasing. Yes. This is also said to be increased. Correct or not?
Yes, yes.
Both are connected same points.
Okay. Initially E2 also increase.
Yeah, V will be definitely more than E2. That's the reason we are taking V is equal to E2 plus ISY.
To maintain 400 volt, we have to decrease that E2.
Yes. Because this E1 dash we made it as a 450 say, then E2 has to be decreased again, then only you will get V say. Correct? Yes.
Then at that point, why sir you not taking out E1 dash also if it decreases, then also 400 volt can be achieved.
That's what E1 dash is next you say only E1 dash increase, definitely V will increase na? Yes. But to maintain the same way, E2 dash you have to decrease. You can write E2 dash that is going to be reduced. You will get again 400. Right?
It will be magnetized, na? Means it also definitely going to
internally what is then still you decrease, it is going to be magnetized. Okay, but at the same time, second time what is happening? Yes, good point. So what will happen, you know, that ISY is equal to E1 dash minus E2 divided by ZS1 plus ZS2. Of course, both are equal means 2 ZS. What you are doing is, when excitation of second machine is reduced, listen, very good point. When excitation of second machine is reduced, E2 definitely reduce. Correct? E2 reduce. But E2 reduce means what happened? ISY, tell me. ISY will increase.
Yes.
When ISY is increased means on the first machine, still more demagnetization. It is reducing. More demagnetization. On the second machine, of course, it is magnetization. But the difference is decreasing. Difference is going to be reduced. It is magnetization, okay, but at the same time you have reduced it. Reduce it. We are decreasing.
Again balance. Again balance means
don't think again. Increasing. See, when this is decreased means this is some 350 volts say. For example, it is some 350 volts. 350 volts say. But when excitation is increased, it is not 400. It will be some 430 volts say. 430. but this is at the same at a demagnetization. It is not 350. It is also again going to be increase a bit. How much it is? Some 370 say. But when compared with earlier 400, it will be still less. Right? These things we cannot identify. If problems are given, then we can say we can answer. That's the reason I am not much focusing on the numerical values.
Yes,
Right?
yes.
Yes. Yeah. Now let us go to the next topic. Hello, anyone? Last. Hello. Yeah. Fine. Let us see the next topic. Next one is effect of change in. Next one, effect of change in mechanical power input. Case 2. Case 2 is effect of change in mechanical power input. Effect of change in mechanical power input. Mechanical power input, or that is nothing but prime mover input. That is prime mover input. Prime mover input. Effect of change in mechanical input or prime mover input. Two machines are connected in parallel. Two machines are connected in parallel. ZS1 and ZS2. Yeah. Yeah. See, this is E1. Generator EMF is E1 and this is E2. E1 and E2. This is terminal voltage V and frequency F. Say frequency F. Frequency F. If two machines are given, this is prime mover torque in this direction, prime mover torque, and say this is omega. It is rotating at what speed? Some speed 1500 RPM, say 1500. This is also omega TPM. It is rotating at 1500 RPM, say 1500 RPM. If it is a 4-pole machine, its frequency is 50 hertz. 4-pole machine frequency is 50 hertz. Just for example, I am taking 1500 RPM. You can take any speed, any speeds. Yeah. Again, take its phasor diagram. This is E1. See, this is E1. Initially, both are same. E1 and this is E2. E1 and E2. E1 and E2. With respect to local circuit, there is no synchronizing current. There is no synchronizing current. Now, if excitation of machine 1 is increased, not excitation, sorry, prime mover input of machine 1 increases. Listen. If I am increasing prime mover input of first machine, dear students, when prime mover input increases, what happened? Its speed will increase, na? When prime mover input is increased, its speed will be increased to some 1600 RPM, say 1600 RPM. So first machine is rotating faster. 1600 RPM. Mean its frequency is increased. when primary input of first machine is increased, mechanical power input of first machine is increased, its speed will increase. When its speed increase, its frequency also will increase. Its frequency also will increase. When first machine frequency is increased, second machine frequency also has to increase. Then only stable parallel operation. For stable parallel operation, what is the condition? Set frequency must be same. But what we are doing, I am increasing only mechanical power input of first machine. So therefore, its speed increase, its frequency is increased. Now, how second machine frequency will increase? How set frequencies are equalized? How stable parallel operation takes place? How frequency stability is achieved? That can be done again by the synchronizing power. Synchronizing power will comes into picture, but this time the synchronizing power is going to be active power. Synchronizing power will be active power. Because prime mover input, we are giving prime mover input is increased, na? And when prime mover input is, it is active power. When mechanical power is active power, then synchronizing power also will be active power. Earlier it was excitation. Excitation is related to flux. Excitation increase earlier, it is a flux. Then flux component only will come. That is a reactive component. But now it is active component. So when prime mover input is increased, then also synchronizing current will come into picture, and that is maintain the synchronism. It will equalize the set frequencies. Let us see how. What I am doing is, if mechanical power input of first machine is increased, then when mechanical power input of first machine is increased, E1 will shift by its phase. E1 will shift, na? Yes. E1 will shift its space. So therefore, this is E1. Delta increases. E1. When prime mover input is increased, when mechanical power input is increased, then active power increase. Then active power P increases. But what is P? P is equal to EV by XS sin delta. That will increase. Therefore, delta will increase. Earlier this is E1, na? E1 phasor will shift. Then there is a potential difference. Earlier there is no potential difference, both 400. But now these, due to this vector potential difference, then this is a vector potential difference. This is ESY, synchronizing voltage. The resultant synchronizing voltage, ESY. Now when that is ESY, this will be the ISY. This is ISY. The synchronizing current always lags that ESY by 90 degrees. This is ISY. Such that ISY lags this ESY by 90 degrees always. ISY. Okay. And this ISY is almost in phase with first machine. Na? Yes, ISY is almost in phase with first machine. But ISY is common. Synchronizing current is coming. Synchronizing current again, it is coming, circulating inside of the machine. Synchronizing current is delivered by the first machine, absorbed by the second machine. So first machine is how it is acting as a generator. Second machine is acting as a motor. Why? Because ISY is in phase with E. ISY and both are in same phase, means that machine acts as a generator. But when current is in phase opposition with E2, that machine acts as a motor. Okay? First machine delivering the current, second machine is absorbing. Current is opposite direction to that E2, na? Yes. But when first machine is acting as a generator, then it will develop the torque. Its torque will be in opposite direction. And that to be, first of all, the synchronizing power is active power. Synchronizing power is active power or reactive power? Because E1 is almost in phase with ISY. Power factor angle is nearly zero. Okay. Yes. See, ISY is in phase with E. So therefore, I can write synchronizing power is equal to E1 into ISY cos 0. E1 into ISY cos 0. For second machine, E2 into ISY cos 180. Cos 180. Therefore, when excitation of machine 1 increased, not excitation, when mechanical power input or prime mover input of machine 1 is increased, then delta increases. Therefore, delta increases. And that ISY is almost in phase with E1. And that ISY is almost in phase opposition with E2. And the synchronizing power PSY. Synchronizing power PS a first machine is equal to what? E1 into ISY cos 0, almost cos 0. Nearly 0, na? Yes. That is equal to what? E1 into ISY. Similarly, PS2 is equal to E1 into ISY cos 180. Cos 180 means minus E2 into ISY. This will be minus E2 into ISY. So power is negative. First machine power is positive. Power positive means it acts as a generator. But this acts as a motor. Power is negative. It is taking the power, but this is giving the power. First machine acts as a generator. Second machine acts as motor. But the synchronizing power is the active power. Synchronizing power is active power. It is not reactive power. If you find QS1, is equal to E1 into ISY sin 0. Sin 0 is equal to 0. But QS2 is equal to E2 into ISY, that is sin 180. It is also equal to 0. Therefore, synchronizing power is not the reactive power. Synchronizing power is not the reactive power. That is only active power. Synchronizing power is only the active power. It is not reactive power. These statements, it is fixed. Yeah. So, first machine is acting as generator, second machine is acting as motor. They are developing the active power. And when active power is there, it will develop the torque also. Na? Active power will develop the torque. Reactive power will produce the flux. So see, this active power, first machine acting as a generator means it will develop the synchronizing torque. In which direction synchronizing torque? Tell me. In generator, synchronizing torque is in opposite direction. This is TSY. Synchronizing torque is in opposite direction. But in first machine, synchronizing torque is in same direction. TSY is in same direction. Because in generator torque opposes, in motor torque AD. In motor torque support the rotation. Because first machine acts as a generator, synchronizing torque decelerate the first machine, accelerate the second machine. Because second machine is acting as a motor. In motor, torque will be in the same direction of rotation. Generator torque is in opposite direction. So what that synchronizing torque is doing? It is braking action taking place. So it is decelerating first machine, accelerating second machine. Then what is the speed is going to be? Its speed will be again, speed will be almost, both will be settled with same speed. How much speed? Say, it may be settled at some 1550, say, its speed may be settled to 1550, its speed also settled to 1550 RPM, 1550. And finally, both are settled at same speed, 1550. Okay, yes. Both are stabilized, that is important. What will happen, you have started 1500 RPM onwards, 1500 RPM. But now, when primary input is increases, its speed increases. But immediately synchronizing torque will comes into picture. It is decreases the first machine speed and it is accelerate the second machine. Its speed also increase. But both are settled with the same speed. And finally, the speed is increased, set speed is increased, frequency also will increase. For example, earlier its frequency 50 hertz, say 50 hertz, but now the frequency will increase. The frequency will increase to some 51 hertz, say. So important conclusion, if mechanical power input of any one machine is increases, set speed will increase. Set speed will increase. Set frequency will increase. Set frequency will increase. Now tell me, and to maintain the same frequency, I want 50 Hz frequency. What to do? Again, I want 50 Hz frequency. What to do? Decrease the primary input of second machine. Primary input of second machine has to be decreased. Opposite action. When second machine frequency is increased or decreased, then its speed will reduce. And again, synchronizing current will increase. Such that, so more braking action. When you are decreasing the speed, for example, when you are decreasing the speed means its speed decreases, then synchronizing current will increase. Phasor difference is increasing. You are doing like this, and again it will be lagging. Opposite action you have to take. Opposite action. Okay? Yeah. Both will increase. But when to maintain the same frequency, you have to reduce. Okay? Synchronizing power is equalizing the speeds. When speed is increased, synchronizing power is decreasing. And other machine it is accelerating. So that set speeds will be equalized. Yeah. Let me brush up all these conclusions. After that, I am going to write all these points. Dear students, listen. When mechanical power input of machine 1 increases, then synchronizing power will comes into picture. That is the active power. Synchronizing power, active power. And with respect to machine 1, with respect to synchronizing power, machine 1 act as a generator, machine 2 act as a motor. Then the synchronizing torque decelerate the first machine and accelerate the second machine, such that set speeds are equalized, set frequencies are equalized. But if mechanical power input of any one machine is increases, set frequency will increase. Set speed increases, set frequency will increase. But to maintain the same frequency, what to do? Decrease the mechanical power input of other machine. Decrease the mechanical power input of second machine. Okay? Yeah. Let me write all these conclusions. If the mechanical power input of or primary input of machine 1 is increased, machine 1 increased, then synchronizing power will comes into picture. Synchronizing power will comes into picture, which is active power, which is active power, which is active power. Next, with respect to synchronizing power, machine 1 acts as generator, and machine 2 acts as motor. Machine 2 acts as motor. Machine 2 acts as motor. Therefore, synchronizing torque, TS, synchronizing torque TS, decelerate the first machine, of whose prime mover input is increased, of whose mechanical power input is increased, and accelerate the other machine. Such that set speeds are equalized, set speeds are equalized, and set frequencies are equalized. For stable parallel operation. If mechanical power input of any one machine is increases, if mechanical power input of machine 1 is increased, then set speed will increase. Set frequency will increase. But to maintain if you want to maintain the same rated frequency, decrease the prime mover input of second machine, decrease the mechanical power input or prime mover input of other machine. Okay, these are the conclusions. Now you forget about the numerical values. Numerical just for explanation I have taken. So this is about no load condition. These are about no load condition. Okay. Now full load conditions also same thing. And in other words, full load conditions are going to be very, very simple. Let us see. Now load condition. Let us discuss under load condition. Load condition. Taken? Yeah. Load condition. First I will take effect of change in excitation. Load conditions. Load condition. So load conditions, load is connected. ZS1, ZS2. Okay. So both are commonly connected with a load. Common load is connected. Fine? Yeah. But when load is there, both are supplying. See, it is delivering the current of IA1 to the load, it is going, and second machine is delivering the current IA2. That is also going to the load. So both are going to the load. Both are going to the load. Total current how much? IA is equal to total current IL is equal to IA1 plus IA2. Load current IA1 plus IA2. Of course, both are vector sum. Since both are AC currents. And this is E1, this is E2, say E1, E2. This is the terminal voltage V, frequency F, terminal voltage and frequency F. Terminal voltage and frequency. And initially, both machines are sharing the loads equally. E1 is equal to E2, say initial conditions. Initially, E1 is equal to E2. E1 is equal to E2. And power factor of first machine. E1 is equal to same and IA1 is also equal to IA2, say both currents are equal. Power factor of first machine also equal to power factor of second machine, take it. When current power factor is same, active power of first machine is equal to active power of second machine, KW1. KW1 is equal to KW2 and KVR1 also equal to KVR2. The reactive powers are equal. And KVA ratings also I am assuming same. KVA1 is equal to KVA2. So this is the initial conditions. These are the initial conditions. Initial conditions. All these are initial conditions. Right now, both are operating with this. E1, E2, currents all they are equal. Same rating of the machines. Of course, it is not mandatory. Not mandatory. Two machines not necessary to be same rating, and their speeds also may be different. I have taken for understanding purpose both speeds same. And here also I am taking KVA ratings also same. But it may be different also. If a numerical problem is given, then we can show the answers with the calculations. But for while theoretical discussion, let me take both are having same KVA ratings. Okay. So they are sharing the load equally. Dear students, IA1 is equal to IA2. Power factors are same. Their active power sharing is same. Reactive power also sharing equally. Their ratings are also same. Now, for example, 100 kilowatt load is there, say. Both are 50-50. Both are sharing equal. And 50 kVR, 50 kVR. Their load sharings are same. Next, what we are going to do is, if excitation of first machine is increased, what happened? All these things, how they will be changes? They are itself objective questions. When excitation of first machine changes, what happened E1 and E2? What happened current? What about power factor? What happened active power sharing? What about the reactive power sharing? And what is the KVA loading on the machine? All these will be changes. How they are changes that we are going to see. So first let me take case 1, effect of change in excitation. First one is the effect of case 1 is Effect of change in excitation under load condition. Effect of change in excitation. Effect of change in excitation. Effect of change in excitation. See, what we are doing is excitation of the first machine is increased, field current. Excitation of first machine is increased means E1 will be increases. E1 increase to E1 dash, say. E1 increase to E1 dash. Then there will be synchronizing current. Then there will be synchronizing current. ISY will comes into picture. ISY will comes into picture. Okay. And that ISY is delivered by the first machine. ISY is absorbed by the second machine. ISY will be absorbed by the second machine. Okay. Yeah. Now, then this ISY is it active power or reactive power? ISY, can you tell me, is it active current or reactive current? ISY is it IA sin phi or IA cos phi? IA sin phi. It is reactive current. Already we have established conclusions. When excitation changes, synchronizing current will be reactive current. Reactive current. Reactive current or reactive power. And this reactive power, what it will do? It will demagnetizes the first machine, magnetizes, same story. That is same. When excitation of first machine increases, set terminal voltage increases. Whatever the conclusions we made under no load condition, here also totally valid. Valid. But what happened? Powers that we are going to mainly focus. Yeah. See, this ISY is the active reactive component, but that is aiding with IA1. But of course, this IA may be having two components. If your load is inductive load, say IA1 will have IA cos phi and IA sin phi. IA1 cos phi, IA1 sin phi. Second machine also IA2 cos phi plus J IA2 sin phi. The IA is having two components, say, if load is inductive. But the synchronizing current is only IA sin phi component. And this IA sin phi component will add to the I sin phi component of armature current. Therefore, net IA sin phi component increases. When net IA sin phi component increases means VI sin phi increases and reactive power increases. In other words, the synchronizing power is reactive power. It is aiding with the first machine. It will supply more reactive power. Reactive power of first machine is increased. But what happened? Reactive power of second machine is ISY opposing the IA2. IA2 sin phi is going to the load, but this ISY sin phi opposite direction. What happened? Net IA sin phi component reduced. Net reactive current is reduced. Opposing. So this is one upwards, one downwards. Reduced. So reactive power sharing is reduced. So reactive power sharing of first machine is increased. Reactive power sharing of second machine will reduce. But no change in its active power sharing, dear students. No change in its active power sharing. Why? Why? Because the synchronizing power is only reactive power. So only reactive power is coming, that is aiding for the first machine. Therefore, net reactive power is increased. But for second machine, opposing, net reactive power is decreased. So there is only change in its reactive power sharing, but no change in its active power sharing. Active power is same. Reactive power only changes. And KVR1 increases, KVR2 decreases. So let me write the conclusions. The conclusions are, yeah, if excitation of machine 1 is increased, effect of change in excitation, if excitation of machine 1 increase, if excitation of machine 1 is increased, then excitation is increased, that is E1 increases to E1 dash, say E1 increases to E1 dash, then the synchronizing power will comes into picture. Then the synchronizing power will comes into picture. It comes into picture, which is reactive power. Which is reactive power. Reactive power. Okay, reactive power. And the synchronizing power. Synchronizing power is aiding. Synchronizing power is aiding with first machine, with machine 1, and opposing second machine. Opposing second machine, machine 2, opposing machine 2. Therefore, reactive power sharing of first machine is increased. Reactive power sharing of machine 1 will increase, but machine 2 will reduce. Reactive power sharing of machine 2 will reduce. Reactive power sharing of machine 1 will increase, machine 2 will reduce. But no change in its active power sharing. No change in active power sharing because synchronizing power is only reactive power. No change. So the general statement is effect of change in excitation causes. When excitation changes, what happens? General statement. Effect of change in excitation causes only change in its reactive power sharing, but no change in its active power sharing because synchronizing power is only the reactive power. Synchronizing power only reactive power. So general statement is effect of change in excitation causes. Effect of change in excitation causes. Effect of change in excitation causes only change in its. Only change in its reactive power sharing. Only change in its reactive power sharing. Reactive power sharing. But no change in its. But no change in its active power sharing. Active power sharing. Because active power sharing. Because the synchronizing power is only reactive power. Synchronizing power is only the reactive power. Synchronizing power is only the reactive power. Yeah. So now let me give conclusions in table. No change in its reactive power. No change in its active power. Only change in its reactive power. I'm writing in a table. For machine 1, machine 2. Initially both are same. Machine 1 and machine 2. Machine 1 and machine 2. There is no change in its reactive power sharing. There is no change in its reactive power sharing. It is KVR. First I am writing. KVW is equal to KW1 is equal to KW2. No change. KW1 is equal to KW2. No change. Let me use with the black color. Machine 1 and machine 2 for better visibility. See, for machine 1 and machine 2, KW1 is equal to KW2. No change in its reactive power sharing. KW1, KW2 same. But KVR of first machine, KVR1 is increased, KVR2 is reduced. KVR2 will reduce. What happened? KVA1 increased. KVA2 will decrease. Because why KVA? KVA is equal to square root of KW square plus KVR square. Therefore, when KVR is increased means KVA also will increase. KVA loading will increase. It will take more reactive loading. Okay. Yeah. KVA1 will increase, KVA2 decrease. What happened current? IA1 will increase. Earlier both are same, na? IA1 increase, IA2 will decrease. IA2 will decrease. Why? Why? Because ISY is aiding with the first machine, na? Yes. Even that IA is equal to, IA will have two components. IA cos phi plus J, IA sin phi, plus or minus, of course it is, plus or minus. Magnitude if you take, IA cos phi square plus IA sin phi square, IA sin phi square. In this, which component is changing? Is it IA cos phi or IA sin phi? IA sin phi component only changing. This is change. IA sin phi component only will change. Right? Yeah. So first machine IA increase, na? IA sin phi is increased. When IA sin phi is increased, it means definitely IA also will increase. IA sin phi, IA increase. Second machine IA sin phi is reduced. Therefore, IA also will reduce. IA also will reduce. What about power factor? Power factor of first machine will reduce. Why? Because reactive power is increased, na? Reactive power increase. Power factor of second machine will increase. Why? Because power factor is equal to active power divided by kVA. Active power divided by kVA. That is equal to kW divided by square root of kW square plus kVR square. In other words, power factor is proportional to active power, inversely proportional to reactive power. But first machine, reactive power is increased, therefore power factor will reduce. These are the statements. Okay. But all these statements, if excitation of machine 1 is increased, that is E1 increases, okay, then these conclusions are valid. Instead of that, if I may ask, if excitation of machine 2 increases, conclusions are just reverse. Okay. Yeah. Now reactive power is shifted on which machine? First machine, reactive power is shifted. Why we will do like this? If you want to reactive power sharing. For example, dear students, listen. Initially, both are sharing same reactive power. Initially, both are 50 kVAr, both are sharing initially. Listen. But now I want to shift most of the reactive power onto the first machine. Then what to do? Increase the excitation of first machine. So therefore, it will take more reactive power. And reactive power on the second machine will reduce. Because excitation increases, synchronizing current increases. It is opposing, yes. It will take more reactive power. It will less reactive power. But when excitation of first machine increases, terminal voltage will increase. But to maintain the same thing, what to do? You have to decrease the excitation of second machine also. Why? Because its reactive power burden has reduced. Reactive power is decreased. ISY reducing reactive power burden. Therefore, that much excitation, field current is not required. Therefore, you have to reduce the excitation to maintain the rated terminal voltage. If only excitation of first machine is increased without doing anything for second machine, definitely terminal voltage will increase. But to maintain the same thing, you have to decrease. That is what practically they will do. Automatic field regulator AVRs are there. If you want to increase the first machine, simultaneously it will decrease, such that terminal voltage is always maintained rated value. Loads required rated value. If voltage is increases beyond a particular value, insulation failure takes place. Over voltages also we do not like. Fine? Yeah. See here, to shift the reactive power, from machine to shift the reactive power from machine 2 to machine 1. What to do? Machine 2 to machine 1. Machine 2, machine 1 to machine 2 to machine 1. Increase the excitation of machine 1. Increase the excitation of machine 1. But the over-excited machine will take more reactive power. When excitation is increased, it will take more reactive power. Okay? Yeah. Next. These are itself state direct objective questions on this table. Similarly, effect of change in mechanical power input. Effect of change in mechanical power input. Let us see. Case 2 is effect of change in mechanical power. Second case, case 2. Effect of change in mechanical power input or prime mover input. Effect of change in mechanical power input or prime mover input. Prime mover input. Yeah. The no diagram is required. Diagram is same. First diagram is same. Now when mechanical power input is increased, see under this heading, here students, see, when mechanical power input of first machine is increased, then also synchronizing power will comes into picture. But this time the synchronizing power will be active power. Already we have seen. This ISY is a I cos phi component. I cos phi component, it will aid to the first machine I cos phi component. Therefore, net I cos phi component, active component of the current of first machine will increase, but it will opposes the second machine. The active component of the current will reduce. Therefore, active power sharing of the second machine reduce, active power sharing of the first machine will increase. So, effect of change in a mechanical power input, when mechanical power input of any one machine increases, then there will be change in its active power sharing, but no change in its reactive power sharing, because synchronizing power is only the active power. Synchronizing power is only active power. That's the reason active power difference only will come when mechanical power input changes, active power differences. But when excitation changes, reactive power differences. That is the main key point. Okay. So active power sharing increases first machine, active power sharing will decrease. Yeah. If mechanical power input of mechanical power input or prime mover input of machine 1 is increased, then the synchronizing power will comes into picture. Then the synchronizing power will comes into picture. Synchronizing power will comes into picture, which is active power. Which is active power. And the synchronizing power aiding with the synchronizing power aids with machine 1 and opposes the machine 2. Opposes the machine 2. Therefore, opposes the machine. Therefore, active power sharing of machine 1. Active power sharing of machine 1 will increase. will increase, but active power sharing of machine 2 will decrease. Machine 2 will decrease. But no change in its, no change in its reactive power sharing. Reactive power sharing. Because synchronizing power is only active power. So in other words, effect of change in mechanical power input or prime mover input. Effect of change in mechanical power input or prime mover input causes only change in its active power sharing. Change in its active power sharing. But no change in its reactive power sharing. Because synchronizing power is only active power. Because synchronizing power is only active power. Synchronizing power is only active power. Now let us tabulate all these conclusions. Table. Initially both are equal, na? Now they have changed. Let me give you table. Okay. For machine 1 and machine 2, we are writing the conclusions if the mechanical power input of machine 1 is increased. For that we are writing the conclusions. First, there is no change in its reactive power sharing. KVR1 is equal to KVR2. Before changing, before disturbance, after disturbance also same. There is no change in its reactive power sharing. But KW1 of first machine increases. KW2 second machine active power will reduce. And when active power changes also, KVA1 will decrease. Anyone, KVA1 is equal to KVA square. KVA square plus KW square, KVR square. Anyone increases, KVA2 will decrease. What happened current? IA1 will increase because reactive component increases. What about IA2? Will decrease. And power factor of first machine. Power factor is proportional to active power, inversely proportional to reactive power. But active power is increased in the, therefore power factor of first machine increase. Power factor of second machine will decrease. Okay. So these are the important conclusions. Fine? Yeah. So if you want to share the active power, it is load sharing, dear students. You have taken this, na? Listen. Two alternates, alternator 1, alternator 2 is there. Both are there. Alternator 1 and alternator 2. Going back to our original diagram. So alternator 1 and alternator 2 is there, na? Yes. Total load is 50 kilowatts, say 50 kilowatt, 100 kilowatt. 100 kilowatt, initially both are taking 50 kilowatts, both are half of it is sharing. But now I want to share the load on the first machine. What to do? Load on the first machine means increase its mechanical power input. Increase its mechanical power input and decrease the mechanical power input of other machine. When its mechanical power increase, it will take more load. More load. But on the second machine, it is reduced. On the second machine is reduced. But to maintain the same thing, what to do? Active power loading is reduced. Na? You are increasing mechanical power in the first machine. It will take more active power. But net active power constant. Then active power availability on the second machine will reduce. Okay. For example, to say, initially both are 50 kilowatts. This is 50 kilowatts. This is also 50 kilowatts. Right. But now I have increased. This is taking 70 kilowatts. What happened on this? This will reduce 30 kilowatts, total 100 kilowatts. Okay. On second machine, active power loading is reduced. If you keep same prime mover input, both are going to be accelerate. This will accelerate, this also accelerate. Why first machine accelerate? Speed increases. Why? We have increased mechanical power input. Second machine also will accelerate. Why? Load is reduced. It is also accelerate. Both are accelerate. Set frequency will increase, no doubt. If mechanical power input of any one machine increase, set frequency will increase. But to maintain the same thing, what to do? Decrease the mechanical power input of second machine. Why? Because net load on that machine has reduced. Na? When net load is reduced means decrease the mechanical power input also. Because load is reduced means correspondingly you have to decrease. Then to maintain the rated terminal voltage. Rated frequency. Fine? Yeah. The questions are same. Two machines are connected. Mechanical power input of machine 1 increases. What happens at frequency? Increase. No load condition, whatever you can increase. Okay? Increase. This, let me write here. Here also, if you want to write, frequency will increase. F1 increases and also F2 increases. F1 will increase. F2 frequencies will increase. But to maintain the same thing, you have to reduce. F1, F2 increase. Both will be equal, of course. F1 increase, F2 increase, but both are equal. Okay. We nearly same. There is mainly change in its speeds, you know. Yes. Okay. Yeah. The point is to shift the active power from machine 2 to machine 1, increase the mechanical power input. Listen, lastly, yes, we will go for a break. Just for 2 minutes, 2 minutes, wait for some time, then we'll go for a break. Here, active power sharing is depends on the prime mover input. Reactive power sharing is depends on the excitation. Therefore, reactive power is controlled with excitation. Active power is controlled with prime mover input. And active power sharing is also depends on the prime mover characteristics also. Write this. Reactive power sharing. Reactive power sharing is depends on. Reactive power sharing is depends on excitation. Therefore, reactive power is controlled with excitation. Reactive power is controlled with excitation. Reactive power is controlled with excitation. And active power sharing. Active power sharing is depends on prime mover input. Depends on prime mover input. Active power sharing is depends on the prime mover input. Therefore, active power is controlled. Active power is controlled with prime mover input. With prime mover input. And active power sharing is depends on the prime mover characteristics also. Active power sharing active power sharing is also depends on the prime mover characteristics. Prime mover characteristics, or that is turbine characteristics. Turbine characteristics. Active power sharing is also depends on the turbine characteristics, prime mover characteristics. And for proper sharing of load, and for stable parallel operation, the turbines should have drooping characteristics. Drooping characteristics. For proper sharing of load, they should have drooping characteristics. Drooping means drooping characteristics. Drooping means like this. This is frequency or speed, F or speed also. And this is load. This is the load. So frequency versus load, the characteristics are say like this. This is turbine characteristics. See, this is for machine 1 and this is machine 2, turbine characteristics, machine 1 and machine 2. But both will operate with common frequency. Based on that, the load sharing of first machine is P1 and load sharing of second machine is P2. Okay, P2. This is having some X percentage drooping. This is having Y percentage drooping. Y percentage drooping for proper sharing of load. But the machine which is having less drooping will share more load. The machine with the less drooping will share more load. Less drooping will share more load. For example, still, if you want, see, less drooping, see. Then what is going to be happen? This one, it will share like this. This will share more load. Right? Then you can observe clear. Less. Now, why to have drooping characteristics? Why they should have drooping characteristics? Otherwise, what happened? Machine 2, it will have some Y percentage. Why drooping characteristics means for stable parallel operation. Otherwise, for example, if it is second machine is having still less drooping, still it is having less drooping, what is going to be happen? Tell me. If it is having still less drooping, this is still less drooping. What will happen? It will take still more load. Of course, they may be settled with some other frequency. What happened? On the second machine, power has reduced. This is P1 dash, say. P1 dash, but this is P2 dash, has increased. Yes. Still less drooping means it will share more load. Okay. More load. load on the first machine is reduced if it is having still less drooping. Like that, if it is no drooping, say, can you tell me what is going to be happen, dear students? If there is no drooping, what will happen? What will happen? If there is no drooping means first the machine 2 only will share entire load. The machine 2 only will share entire load. Machine 2 only will take total load. It will not give any choice for the machine 1. Then machine 2 taking more load means that machine is going to be unstable. Because overloaded, it is going to be overload and that machine will be unstable first. If the machine is not having turbine characteristics, no drooping means that will be unstable first. That's the reason both should have drooping characteristics. Okay? Yeah. And after the break, we are going to see the objective questions and also problems. Theory part is completed, 2 alternates in parallel. And we are going to do the problems as well as some theoretical questions also we will see. Right? Any doubts? Okay, just let me attend to some doubts. Any doubts are there? Tell me, some of you are raising your hands. Hello?
Hello.
Tell me.
Sir, if we are increase the prime mover load,
Time or input.
then what is the change in that machine 2? That is, what is the change in the del angle? Because in the first case, del angle increases. Here, del angle decrease in the motor. Machine 2.
Machine 2?
Del angle will be.
Yeah. Reduce, but both will settle with some angle. For example, the second, if you take on both sides, same side, this is E1, okay? This is E2, say. E2, both are in same direction, right? Yes. And when excitation of first machine is increased, what will happen? Prime mover input of first machine, prime mover input. This is E1, E2, say. E1, E2, both are equal. Magnitudes are equal. E1 is equal to E2, right? And when excitation of input of first machine is increased, then it will be E1 will increase. E1 is shifted to here. E1 is shifted to here. Del has increased E1. This is a delta. When compared with first case, this is a delta. Then again, this is the potential difference between E1 and E2. Due to that potential difference, this current will comes into picture, ISY. Okay, but this is ISY for first machine. ISY with respect to second machine, you have to take reverse for machine 2. This is for machine 1. Now tell me, what is your doubt?
What is that E2 and ISY? That angle is machine 2.
E2 ISY nearly 180. E2 and ISY angle is nearly 180. Okay, E1 and ISY almost in phase. You have taken. And your doubt is with delta. First machine del increases definitely. Okay. Second machine
del also.
It is taking less load. Less load means del will reduce.
Yes.
That will be with respect to V. You need to take V. I am comparing only with E1 as a reference. With respect to that E2, what is happening? Actually, del is the angle between V and E. V and E. E1 and V, E2 and V. But here I am comparing with internal voltages E1 and E2. If I take E2 reference, when compared with E2, E1 will be more angle.
Okay.
Okay.
Hello, sir.
Sir.
Hello, sir.
Sir, here in this thing, like right now you mentioned that when load increases, speed also reduces.
Where?
And the droop characteristics.
Load increases.
So as load is increasing, we are seeing the frequency of operation, or we can say the speed is reducing.
No. Load increases in the sense first we are increasing the prime mover input. That's the reason it is taking more load.
Yes, sir. If you see by that logic also, like what you said previously, when you're increasing the prime mover input, the speed of first machine will increase.
Yes, yes.
And since on the second machine there is much further lesser load, that speed also will increase.
Yes.
So
Yes.
then in that sense, the overall speed is increasing and then frequency should increase, no, sir? If in this case load is
Very
increasing.
good. That's what. That is what I told you. You are correct exactly. That's what only I have told.
So, but in this case, if you look at the droop characteristics, as load is increasing, frequency is reducing, no, sir?
And that will definitely occurs. No. Both are, these are the original characteristics of that. Drooping characteristics we are taking. They are the characteristics of the turbine. When load increases, its speed has to reduce. But they both will settle with some particular frequency. Both has to be settled with some particular frequency. Na?
Yes, sir.
Earlier, both are operating at 1500 RPM. See,
Yes, sir.
the prime mover input increases, it has become 1600 RPM. 1600. But synchronizing power is coming into picture, it is decelerated. It is becoming 1550. Speed is reduced. Compared with 1600, it won't increase whatever you have given proportionally. It is reduced 1550. Other machine increase 1550. Both are settled with same frequency. That is what we are taking.
Okay, sir. Okay. This is so these are the characteristics of the turbine.
Yes. Turbine, exactly. Turbine. Okay.
Thank you, sir.
Mainly problems will be based on these characteristics that we are okay. Tell me. Hello.
Hello, sir.
Yeah. Tell me.
Sir, in any situation, the case 1 or case 2, if there is a rise in the excitation or the mechanical power input, then there will be a synchronous current in the loop. After settling the terminal voltage at a particular level, is there presence of this synchronizing current or not, sir? It will be going to zero or it will be present in the loop?
No. It will exist. It will exist.
So then there will be some mechanical copper loss will be there in the circuit because of this.
These currents will exist definitely. These currents will exist. Then only, in addition to that, what you have to do, this current, when it will reduce, if mechanical power input of first machine is increased,
Yes, sir.
right? Then
Yes,
synchronizing current is more. Synchronizing current is more.
Yes.
Excitation increases. But when excitation of second machine is reduced, then demagnetization, magnetization, their terminal voltages are going to be E2 demagnetize, E1 magnetize, the difference will reduce. But that ISY keep on existing always.
Okay, sir, there will be some presence of ISY.
I don't think it is causes losses.
Okay.
Than the losses, important thing is stability is important. Synchronism.
Okay. Thank you, sir.
Synchronism, it will increase. Okay. Yeah. So let us go for break. Break for 15 minutes. Already we let break for 15 minutes. Okay. Then class will start. At 8:05. సాయంత్రం కూడా ఉందా పొద్దున సాయంత్రం రెండు ఉన్నాయా బర్త్డే రోజు బట్టలు కొనుక్కుంటారు దసరా సండే మళ్ళీ పంపిస్తావు బిట్టు సారీ నాకు ఈరోజు ఇన్స్పెక్షన్ ఉందన్నమాట. తీసుకోరా మరి ఇంకొక మాట అదే
Okay. Okay.